Carbon is the stuff of life. One of the best ways of understanding the carbon cycle is just a whole bunch of things living and dying, and in the process, swapping carbon. Here's the 30-second version. Plants use the carbon in atmospheric CO2 to make sugars and other carbohydrates to grow and reproduce. Lots of those plants end up being eaten by other organisms, supplying them with the building blocks for other biological molecules and fuel. After being metabolized, the carbon returns to the environment in one of several different ways, ending up in the air, water, or the earth itself. From that point, it's released naturally or is extracted by humans, in either case returning carbon dioxide to the atmosphere, and it starts all over again. I am a collection of organic molecules called Hank Green. Organic compounds are a class of compounds that contain carbon, and carbon is this sexy little minx in the periodic table that's, you know, disinterested in monogamy.
Jezebel.
Bit of a tramp.
Hussy.
When I say carbon is small, I mean that it's actually, you know, as an atom, it's a relatively small atom. It has 6 protons and 6 neutrons for a total atomic weight of 12. Because of that, carbon doesn't take up a lot of space. And so carbon can form itself into weird rings and sheets and spirals and double and even triple bonds. It can do all sorts of things that could never be accomplished by more bulky atoms. It's basically, you know, your atomic equivalent of an Olympic gymnast. It can only do all of those wonderful, beautiful, elegant things because it's kind of tiny. I also said that carbon is kind, and that's an interesting sort of thing to say about an atom. It's not like some other elements that are just desperately trying to do anything they can to fill up their electron orbitals. No, carbon knows what it's like to be alone, and so it's not all, please, I'll do anything for your electrons, needy like fluorine or chlorine or sodium is. Elements like chlorine, if you breathe them in, they like literally tear up your insides. And sodium is insane. If you like put it in water, it explodes. Carbon though,
than any other element.
It wants more electrons, but it's not gonna like kill to get them. It makes and breaks bonds like a 13-year-old mall rat, and it doesn't even hold a grudge.
Carbon atoms form chains very, very easily, sometimes millions of atoms long. If you just have atoms that will form 1 or 2 bonds, then you can't build up huge numbers of molecules. But if there's no limit to the number of bonds you can make things that are really long.
So carbon comes as graphite, as diamond, and also as buckyballs or fullerenes.
And most of the molecules that we use for plastics, for pharmaceutical products, for our food, are all carbon compounds.
Carbon's an extremely common element, but it comes in a number of different allotropes, so different forms.
First of all, this is a model of graphite, the material that's in the middle of pencils. And it consists of layers of rings, of hexagonal rings of carbon atoms. That's 6 carbon atoms, and they're joined together in layers. Can you see here there are these purple bonds in between them? You can see they're not very strong. One's even broken here. There's this structure here where each carbon atom is joined to 4 others in this sort of tetrahedral pattern. Tetrahedron is this group, one in the middle with 4 round it. And this is diamond. It's really very strong. We have the famous molecule C60, like a football, 60 carbon atoms. André has put a little one inside here, but forget that for a moment. So you can have this molecule, C60, first discovered in the late 1980s and only isolated in the early 1990s. And there is a very similar molecule, which looks a bit more squashed, which is C70. Now, these are also coloured, but their colour is rather different. And in here, we have the final form of carbon, which are called nanotubes. These are whole tubes made up of hexagons. You have 2 sorts, one which is closed at the end, and this one here, which is open, rather like a basket. You can put things inside it. The final model is graphene, this material that you can peel off graphite with sellotape, sticky tape. And the reason that people get so excited is, first of all, this is a very thin material. It's only 1 atom thick. And you can react the carbon atoms on here with all sorts of different molecules You can make very strong materials. You can start making electronics, carbon computers, things like that. And many people believe that graphene is one of the materials of the future.
Life is only possible on Earth because carbon is always floating around in our atmosphere in the form of carbon dioxide.
It's around us everywhere. We're all carbon. There's lots of carbon in us, in all the hydrocarbons within our body, lots of the structures inside us, and many of the materials that we use every day. In fact, a majority of us use carbon in the form of fuels every day to get to work or to go home.
Without carbon, we couldn't exist. You're carbon, I'm carbon. We have bones made out of calcium, but the important parts, our brains, contain largely carbon. They contain nitrogen and oxygen and hydrogen as well, but carbon's the key.